Okay, yes, as I said, what I tell you is pretty much all I know. We have one unpublished paper on this topic, so it's been sitting for quite a while. So I thought now it's also a good motivation to refresh those results and maybe finally publish them. And okay, and this is what I will mostly talk about. Okay, so but first let's start with an introduction. So yeah, so I will use notations that hopefully the standard notations and that you know. Yeah, so our models will be second order arithmetic. So we will have M for numbers, S for sets. And then using Gödel numberings, we can define everything that is related to formulas, sentences, theories, models, structures in general. So all these things can be formalized, defined in this setting. Okay, so we can talk about consistency, we can talk about completeness, so everything goes through smoothly. And okay, and the first results that appeared here are appeared at the very beginning, pretty much, of reverse mathematics, and those are the obvious things. So basically, I will not go beyond ESI not. So we will only talk. So yeah, we will always be in RCA not, and I will just mention those three, and maybe, but everything will be below this. Okay, so I will not need more than that. Else that I want. Okay, and then basically what we discussed in the very first lecture, the effective version of completeness theorem. This is something that we can take the proof and translate it into reverse mathematical context. So in particular, so I think it was everything done by Simpson. So in RCA naught, like over RCA naught, we have that every, we need to add deductively closed consistent theory model. Okay, so pretty much take the effective Hankin construction that we discussed in the first lecture, and this is what you get. You only need RCA naught to do this. Okay, this deductively closed is important. So in particular, every complete consistent theory has a model, and every deductively closed consistent theory has completion. Okay, completed. And if we take this out, and everything is over RCA naught. Okay, so I will not mention it extra. Okay, so if we have a statement that every consistent theory model, this is equivalent to the Koenig's level. Okay, so what else do we have? We have all those theorems in RCA naught that we discussed, like omitting types. Okay, we can define types and code them, so everything again works smoothly. So omitting types. or realizing types. All of this works for complete theories, complete consistent theories. Okay, and the proof is basically, again, all those effective versions of those theorems that we discussed yesterday or... Okay, a full analysis of what's going on there. Okay, so those were the first results quite a while ago, and then there was some time of silence in this area until the 2000 something. Okay, and then there was a series of papers about reverse model theory. So I will mention just some of those papers, and they're very nicely written and have a wonderful introduction and motivation and all those things. And so if you are interested, I encourage you to look at them, and you'll probably learn maybe more than you learn here. Okay, so let me mention a couple of them. So the first one that I want to mention is by Hirschfeld, Shor, and Sleiman. Called something about atomic theories. Here. Yes, the atomic model theorem and type omitting. So they studied the effective content from reverse mathematical point of view of everything, or of some results that are related to atomic theories, atomic models, things like this. Also using results that I mentioned yesterday about atomic atomic models. And in particular, what they did, they found a principle, reverse mathematical principle, that is not equivalent to any of those, but is quite weak. So it is below RCA0, but incomparable with WKL0. Okay, so it's this a T principle that says that every every complete atomic theory has an atomic model. So this is one of those principles that do not fall into this big five system. Okay, and then there is a not exactly continuation of this work, but some work that was probably motivated by this, again by Hirschfeld, Karen Lang, and Shor. Not about atomic models, but about homogeneous models. Title is, well, induction, bounding, weak combinatorial principles, and I will not write it down, but it's about homogeneous. Homogeneous modes. And there is also some more work done in this area. Harris and by Karen Lang just alone. But it's all like beginning of 2000, like before 2010. Okay, and then there were more results by, I don't know how to really pronounce his name. Do you know? Belanger? Is he Belanger? Yes? Okay, so it's a, yeah, obviously French name, but I don't know if you should pronounce it in a French name. Okay. Yeah. Yes. Yes. So that's why I really don't know. I never asked him. So let's call him David. Okay. For today, just so that I do not embarrass myself. So it's from his PhD thesis. It's 2014. Okay. And so he studied reverse mathematics of results related to countably categorical theories. Okay. And well, in his thesis, he had some open questions. So we, together with Dan Turetsky and Kliway, looked at those open questions, answered one of them, and then also extended all those results to some more stuff. And so I will show you now a table which shows how those are related and to which principles they are equivalent. Like a lot of implications that are equivalent to one of those three. And there are also some open questions, so you are welcome to take a look at it if you also want to and answer some of them. Okay, so this will be me and the way. So this is what I'm going to talk about. Okay, so let me see. Lost in my notes. Okay, so I will write down different properties of countable categorical theories. Properties that characterize countable categoricity are classically equivalent to a theory being countably categorical. And then here I will draw a table and we'll start filling it in the results that we have. Okay. Theorem, classically attributed to Engeler or Relazevsky. Whatever other things that follow, just naturally from known model theoretic facts. Okay, for a complete consistent theory T, the following are equivalent. T is countably categorical. T has a model that is both saturated and atomic. T has a model that is both universal and atomic. All models of T are atomic. For each n each type is principal. And many variables. F for each n, T has only finitely many types in n variables. Basically, here this F, G, H, so those will be actually proved by those people. The Rylnazewski function for T exists, meaning the function that given n outputs the number of types, finite number of types, how many types we have in n variables. And H, a dominating function for this function exists. So a function that for every n outputs that there exists at most as many types. Okay. We are only dealing with countable models. Talking about countable models. This is my level. From the very beginning, so that I only consider. Yeah, so. Okay, so something that I forgot to say here is that basically, when we consider all those theories and structures and everything like this, so in the effective setting from previous lectures, we are thinking about like decidable theories and decidable structures. So here, when we talk about a structure in this reverse mathematical context, we are actually thinking about its complete diagram. Okay, so it corresponds exactly to those results from previous lectures where we talked about decidable theories, decidable models. To know a structure means to know the complete diagram. Yeah. No, I would just stick to countable model. Fine. So let's see what kind of implications do we have here. So we have those A, B, C, D, H, I, B, D, E, H. Okay, some of those implications are obvious, especially almost everywhere where I write RC and not. This is either completely obvious from the definition, going from here to here, or it is a proof of 2-3 lines using one of those. Okay. Okay, so let me just say what was known before as, that is, what was proven by David. This implication is AC naught. Here. Okay, as I said, everything that is RCA node is pretty much obvious. Those ACA node results, at least many of them, are proven using construction of countable categorical theory, such that its Riemann-Zevsky function codes the jump, okay, zero jump. It is a construction that has been known before him, so those are also all the results, again, that were received simultaneously, independently, in the East and in the West. Lutin. Exists decidable countable categorical theory. Such that is equivalent to, you can actually code any computably, whatever computably enumerable set you like. This manner. And well, to some extent, the idea, so the construction is of course different, but the idea is similar to what we had last time with this result with two decidable theory with exactly two decidable models. So you code the complexity of like the zero jump using some predicates, and then you make your structure into a Froissart limit. For this reason, like as it becomes a Froissart limit, so everything, whatever might happen, happens, and everything happens on infinitely many elements, and so on and so forth. And because of this, you have effective quantifier elimination, and because of that, you get completeness, and particularly, you get that it is a decidable and countable categorical theory. So you get this. And one can use this, for example, to get from the result that from the implication from H to G is G naught. So you take this theory, you prove that a dominating function for this theory exists in your model, and then for this reason also the Riemann-Zevsky function has to exist, but it is okay. So I will show you now our results, and I will show you the construction. It is basically motivated and inspired also by this result. So you will see the spirit of this construction also there. So this is what he proved. Okay, so going back to this table, let's fill out some more stuff. So he didn't look at those. He didn't look at those at all. Rated atomic universal, any of those, he didn't really look at those. He looked at the being countably categorical and properties related to number of types in general. So here we can fill out some of those. Some of those cells with much obvious RCA knots. Okay. Those are all this. Okay. And what I'm going to say to tell you is this from A follows the existence of the Rylnatsevsky function. This one. This is what I'm going to show. This is equivalent to ACA naught. Okay. So one direction is obvious. We can prove existence. We can prove existence of this Rylnatsevsky function in ACA naught. Always. So let's code a jump now in such a way that we can prove ACA naught from this implication. So, okay. Theorem over RCA naught. And every countable categorical theory, for every countable categorical theory, the Rylnatsevsky function is how we do this. Okay, suppose this holds. So for every categorical theory, there exists a Rylnatsevsky function. This, in particular, implies that there exist only finitely many types. And like n types or any n. And these finitely many types. This implies WKL naught. Okay, so this was known for us. This is something that we can use. Okay. And now we construct a theory that will show that for each set, the jump of the set exists. Okay. What is the language that we can see? It will be an infinite language. It consists of binary of symbols. I will tell you the arity now. Each en will be of arity 2 to n to the power n. And yet another series of symbols, a group of symbols, R and S. And S. anything in M, and this will be also of arity. Arity in basis. Each En and each Rns has arity 2 to the n. So basically, we think about those ENs. So each En plus 1 is a binary relation on En. Or a relation of arity 2 to the power n plus 1 on the universe. So we will have E0, which will be true on every element of the universe, and then E1. So for example, if we only consider E0, E1, this will be just a graph. If we then consider also E2, so those E2 will be edges between edges of the graph, and so on and so forth. And those R and S, we will think of them as being just unary relation of the corresponding En. Or relation of arity 2 to the n on E0. Fine. So we will call a structure in this language a layered graph. Is symmetric if each of those is symmetric reflexive binary relation. The whole structure is called universe, which is simply E0. Okay, fine. So what do we need now? Now we define an incidence relation recursively, inductively. Basically, it will mean that if we have, if A and B are in E0, then they are incident, even only if they are just equal. Okay, and for higher arities, we just define that element vertex is incident here E n plus 1 if A is incident to X or A is incident to Y. So basically what it means, just if we treat it as a relation, this En plus 1 is a relation of arity 2 to the power n plus 1. This just means that A appears somewhere. So in particular, when we just consider usual graphs, then the incidence is just a usual. Okay, and then just some technical definitions that we need just to be able to prove nice properties about this graph. So we need a definition of dampened layered graph. Means that I need another definition here before I can do this. Notation. So suppose we have a graph like this, then by n dot we denote a subset of En that only consists of such axes, of such tuples that only have all distinct elements. All okay, then dampened layer graph is such that whenever we have a relation En+1, it only can hold on tuples of this form. So we have different elements in the first tuple, in the first layered vertex, and distinct elements in the second vertex. Okay. If E holds only on I. If they do not look like this, then for sure En+1 will not. Fine. Okay. What can we prove? What can we say? Wait, more. So this was a definition. Another definition. Graph was a definition. Graph was a definition. And now we have. Well, now we need to another one definition. Complete bipartite graph. Dampened layered graph is called complete bipartite. Is if every structure of the form En dot En+1 okay, I know, so there's a lot of definitions, but okay, all of those can be described by formulas, so everything still exists in our models. Final property that we will need from our graph is the extension property. complete bipartite layered graph extension property. Okay, I'm too slow, but okay, I'm almost done. As the extension property, if for all finite complete for all finite graphs with this property, A and B, and embeddings F, G, and G from B. So this is a usual idea of A to B. This is the usual idea of the extension. There is an embedding H from B to G. Okay, so now what we consider is the following set of axioms. I will just show you the set of axioms, and it is basically very much motivated by this by this construction. And then you'll just have to believe me that it proves what we need. Okay. So first of all, we say for all x of x. Okay. Obviously, all those E0, E1, and so on form complete bipartite graph with an extension property. Okay, so we can write first order formulas to do this, and then we code the jump into the structure, into the theory, and we do it as follows: if n does not enter the jump at the stage s+1, then we say that for all x in En, we have not R and S x. Okay. And if it does enter at the stage s+1, then we say that, yeah, we have this is a two coloring basically of all vertices here. All x and y in N, if they are related, then they have different colors. And well, then because of all those extension properties and everything being smoothly defined, we can, and using WKL0, we can prove that this is countably categorical, complete, consistent theory with quantify elimination, everything that we need. And suppose now we have a Rylnazewski function. Suppose okay, and then on input n, we search until we find h of n many formulas. With n variables that are satisfiable, pairwise incompatible, and those will be the atoms. And we look at the greatest S, such that we have RNS holding on occurs in one of those atoms, and this will be the stage until where we need to check whether or not N belongs to. Okay, so we can compute the jump. And then using this and using other implications that that are already in the table, we can fill in more gaps here. This completeness. Here. Okay. Okay, so this is now pretty much everything that we know here. What, sorry? A implies H. We don't know, so we need something else. Right. Well, let's see if we have. If we have a yes. So if we have a Ronadzewski function that it is. No, but no. Let's see. This is not enough. So we need to. No. So we do not know that. No, it is not one. So we need to show that if we have this an arbitrary dominating function, if from countable categoricity follows that some dominating function exists, then we need to prove ESI not. We cannot use this because it might be some I don't know this. Okay. We had some consistency results also for other of those, but no definite results. Okay, so this is pretty much everything that I wanted to tell you about reverse model theory. As I said, if you like the topic, look at those papers, and you will see more references there. Let me point out a couple of other references. Thank you.